So this is chapter 8 that we're starting. Actually, we're not starting chapter 8. We did the very first part of chapter 8 before Christmas, and that was the balancing. Okay. So as you're writing this down, these are the general reactions. But the packet that you picked up today, so you picked up the notes and you picked up the packet. There's 5 general types of reactions, and the packet, if you notice, is broken down by types. So as we do a type, you should do that portion of the packet. And then don't try to do the next portion until we learn the next portion. Okay. So today we're going to do composition and decomposition because they kind of go hand in hand because they're kind of opposite of each other. So after we go through the notes, you'll want to do that portion of the packet. So, and then tomorrow we're going to do single replacement and then double replacement on Friday. So those of you who are going to be gone the next 2 days for soccer, you already have everything you need. You'll just need to watch the videos to do that. You know, ideally you should watch them at night and do it, but I know you'll be doing this on Monday night before you come back to school on Tuesday, okay? Because Monday's a holiday. Is everybody aware of that? I know. It's awesome. And so this packet's going to take us through actually Tuesday because since Monday's a holiday, on Tuesday we'll do the last type, which is combustion, which is the last section, I think. And then someone was asking if this is going to be for a grade. Most likely it won't be for a grade, but we'll do a homework quiz over it, okay? So it would be to your benefit to make sure you do it. Also, if you notice as we go through the notes, each type has a practice page to practice the type of reactions. Because right now we're doing them separately and we're saying this is a single replacement, this is a decomposition. But after we learn all the types, you will get a couple of worksheets of them all mixed in, and you have to recognize what type it is and then predict and balance. Okay, so we're going to start out each type and then we're going to mix them all together. So make sure you're practicing as we go along. Also, if you don't practice as you go along, Monday night when you're trying to figure it all out before the homework quiz, you'll get confused because you're trying to do them all at one time. So it helps to, as a new type of reaction is fresh in your mind, work a couple of them so that you can get them solidified in your mind. These up here are just your general forms of the equation. Okay, A plus B makes AB. If you look at decomposition, it's the exact opposite. AB is breaking down. And then, of course, there's single replacement, double replacement, and then combustion. Okay? So let's jump into composition reactions. Okay? Sometimes you'll see them as combination. Sometimes you'll see synthesis. Sometimes you'll see composition. I usually almost always refer to them as composition because it makes sense because it's the opposite of decomposition, because to me they go hand in hand because they're just opposite of each other. The way that you will recognize if something is a composition reaction is it'll make just one product, okay? So you'll have 2 or more simpler substances forming one product only, okay? And I'm not going to insult your intelligence and read what's up there because you're all capable of reading. But these are some guidelines on what some of these things do when they react, okay? One thing on this page that I do want to make note of is it says group 1 and 2 metals will combine to form a salt. What do metals and nonmetals make? Ionic. Okay, so make sure you add that word ionic in there because that's what we've been recognizing. Also, you can just say metals. It doesn't necessarily mean a group 1 and 2 because your transition metals will do the same thing. Okay, the thing about group 1 metals, they're always going to be a +1 in a compound. Group 2 are always going to be a +2. When you're talking about your transition metals, that have multiple charges, generally, one of the exceptions is just copper. Copper is almost always +2, okay? So assume it's +2 unless I tell you it's a +1 for copper. So you assume +2 for copper. It's the more common form, so you might want to jot that down. Generally for your things like iron, lead, tin, those kind of things, generally they'll be the lower of the charges unless they're reacting with something that's highly electronegative. Okay. Remember when we did hydrogen bonding, our 3 most electronegative elements were no orange friends, nitrogen, oxygen, fluorine. So when they react with those transition metals, they tend to make it go to the higher charge. So if iron is reacting with oxygen, it'll tend to be +3 instead of +2. Okay. Now, if you're doing a paper and you gave it to me as +2 instead of +3, I'm not going to count it wrong because I'm not going to hold you to that. I just kind of wanted to make you aware of that. And if you remember it, great. If you don't, that's okay too. Okay. So these 3, there's a mistake here that we need to fix, and that is right here. A metallic oxide plus water will give you not an acid, it will give you a hydroxide. So please mark that out, which is a base. So it will give you a base. Okay? And then again, you can read through those, and I highly encourage you to refer back to those. The biggest hurdle of this unit is people will look at two things reacting together and they just stare at it and they're like, I don't know what to do with this. I'm like, I have given you a whole list of papers saying what things will do with it. For instance, if it is a non-metallic oxide, it tells you non-metallic oxide, make an acid out of it. Okay? If I give you a metallic, oxide plus sulfur dioxide, we'll go look it up and see what it says. Usually I will tell you, or it tells you what it will be. Okay? So let's do a couple of examples in your notes. So if you'll turn the page, there's a whole page of examples of synthesis reactions or composition reactions. So let's do the first one, calcium plus oxygen. It's a metal and a non-metal, so what's it going to make? Yeah, how do I write oxygen when it's by itself? O2. And then, so now they're going to form ions. So I have the calcium ion joining with the oxygen ion. So what should it make? CaO. Okay. Now on your paper, it's giving you the words. You do not have to write the name out. You can just write the formula like this. But it's actually a good way to practice. So what would that be named? Calcium oxide. I'm not going to hold you to that, but it's not a bad way to practice considering you have nomenclature quizzes coming up for the next several weeks. Okay. Let's do, well, number 3 tells you what it makes. Calcium oxide plus water gives you calcium hydroxide. Normally it wouldn't say that. Normally it would just say, expect you to know that a metal oxide plus water gives you a metal hydroxide. We are going to do number 4 because you won't get that on your own. How do I write hydrogen? Plus N2. Okay. Does anybody want to guess what it makes? No. You are close with NH4. NH3. Because it's not going to form an ion when we're doing this. It's going to form NH3. Okay. That is ammonia, which is different than ammonium. Ammonium has a charge, has an extra hydrogen in there. Okay. This is kind of one of those very common equations that you see a lot in chemistry, so it's a good one to just memorize, kind of like the water equation, because you'll see it so much. But now we need to do what to this equation? Oh, we didn't balance the other one. Oh, my goodness.
Yeah, I was wondering.
Whoa, why didn't y'all stop me?
I thought you just that's what you did.
No, you have to balance it. Yeah. My apologies. Yes, let's go back and balance the other one. So I have... So I have to put a 2 here because of the oxygen, and then that forces me to do a 2 there. My apologies. The heat in this classroom is making me not think correctly. Everybody, I know y'all. It's hard to concentrate. Everybody just wants to take a nap now. All right, so let's balance this one. H2 plus N2 is NH3, classic ammonia. 3 on the H, 2 on the NH3. Now it's balanced. Yes, sir.
Okay, so like, if I just had H2 and N2, is there like a way to make it, is it like, do I have to memorize it becoming NH3 or is it like...
For this one, yeah, you kind of do. Most of the time you don't have to memorize them. You can predict them based on the rules. But the 2 nonmetals make a molecular compound, and that is really about the only molecular compound that we're going to deal with in here is NH3 for the nitrogen and hydrogen. Okay. And then let's do one more. Y'all pick. I'll let y'all pick which one. There is not a 21.
Number 5.
Number 5. Okay. Number 5. We have hydrogen and chlorine. How do I write those? Plus Cl2. They are both going to form HCl, hydrochloric acid. And how do I balance that? Put a 2. Now we're done. Okay? So So now let's go to decomposition. Okay? Decomposition is when we have a complex substance and we break it down into two simpler substances. Sometimes that could just be two elements. Sometimes it'll be two simpler compounds. Okay? So here's a couple of examples. Again, I'm not going to insult your intelligence by reading to you. It's not story time with Miss Parker. Okay? You're going to recognize these by the fact that there's only one reactant. They're actually, when they're all mixed together, and I'm giving you all the types, they're the easiest to recognize because it's going to have just one reactant, and it's the only thing that will have only one reactant because it's going to be decomposing. Usually it takes heat or electricity to decompose it. And sometimes if we're saying that, you'll show it with a little heat symbol or electricity over it, but these are just assuming they're there. Okay, so there's three kind. So a while ago we said if you had a metal and a non-metal, you made an ionic compound. Well, guess what happens when you have an ionic compound and you decompose it? Metal and non-metal. They're opposite, basically opposite. Okay. Here we have some other ones. So metal carbonate decomposed into a metal oxide plus carbon dioxide. So if you're using these as your example, let's say on the other ones, I didn't tell you what happens if I added a metal oxide and carbon dioxide. Well, I can flip that around and say it would make a metal carbonate. So you can kind of look at some of these too and flip them for being composition. Okay? All right, let's do some practice on this one. So next page. So let's do the barium carbonate decomposing. How would I write the formula for barium carbonate? BaCO3. Okay, so according to our list, what happens to a metal carbonate when it decomposes? What does it form? Yeah, look at the paper. A metal oxide plus carbon dioxide. So we're going to go ahead and do our CO2 because we know that formula. So that leaves me with barium oxide. How do I write the formula for barium oxide? BaO. Do I need to do anything to balance it? No, I do not. Okay. The next two are also more metal carbonates. So let's go down to, do you want to do zinc hydroxide or iron 2 hydroxide? Your choice.
Iron 2.
Iron 2, okay. So how do I write iron 2 hydroxide? And it says that metallic or metal hydroxides break down into what? So metal oxide and water. So we're going to go ahead and do the water because we know how to write that formula. So how do I write the formula for iron 2 oxide? FeO. BO. Do I need to do anything to balance it? No. I don't.
Does the water or carbon dioxide have to come in the second?
It does not. It's just my habit. Oftentimes people ask, does it matter the order you put it? It does not. Because if I was doing 4 plus 5, same thing as 5 plus 4. It doesn't matter what order I put it. It still equals the same. It's just my habit to put the CO2 and the water on the end, primarily because that's what in the notes it's telling you it makes metal oxide plus water or metal oxide plus CO2. So I try to do it in that order when I'm doing it so when you refer back to it. But it doesn't make a difference. Same thing here. I could have, well, not there because it's only one reactant. But on the reactant side, if there's more than one, it doesn't matter which order. Yeah. Okay? So let's jump down and do one of the chlorates. I'll let you pick which chlorate we do. Sodium chlorate. How do I write sodium chlorate? NaClO3. Okay. And what does it say in your notes about metal chlorates? What do they break down into? So we got the oxygen part, and so I just need to write the metal chloride, which would be NaCl. So now I need to balance that because I have 2 oxygen on one side and 3 on the other. So we're going to do a 2 there and a 3 there. So now I have 6 oxygen, and that means I need to put a 2 there. Always save your balancing for the end. Do not try to balance as you're writing the equations, because your life will get a little complicated if you do. Okay? And then I believe you can, let's do sulfuric acid next. Does everybody have that before I erase? So sulfuric acid, how do I write the formula for sulfuric acid? H2SO4. And that is... Is that what you just said?
Yeah, I put SO3.
And that was one of the homeworks last night. I had both H2SO4 and H2SO3.
I just did it in class.
It's okay.
Darn it.
Everybody makes mistakes. Okay, this is an oxyacid because there's oxygen present. So what does it say about oxyacids? What do they break? Non-metallic oxide and water. So we got the and water over here. So which non-metallic oxide would it make? Which would make the most sense to make our life easier? SO3. It's already balanced when I do that. Okay? Now, I'm going to show you a trick about oxyacids in composition and decomposition. Okay? So I'm going to do a new page here. So let's say I have a non-metal oxide of P4O10 plus water. And if you go look at that, it says that a non-metal oxide will make an acid. It's going to make an oxyacid. Okay? So we only have two choices of what kind of oxyacids we can make with phosphorus and oxygen. What are those two choices? Either using phosphate or phosphite. Okay? We don't know which one yet. We're going to work this at a little separate angle, like backwards kind of. Okay? So either way, whether I use PO4 or PO3, how many hydrogen will I need to put with the formula? What are their charges? They're -3, so I'm going to need 3 hydrogen. So no matter what, I'm going to have H3PO, we're going to say X for right now because we're not sure. Okay? So we're going to do oxygen last in this case only. Normally I always say write the formulas, then balance it. But this one is like an exception. It's going to be better to work a little bit backwards. Okay? So I know that I'm going to have to balance my phosphorus, right? Right now I have 4 on one side and only 1 on the other side. So the only way to balance the phosphorus on the product side is to do what? Put a 4. Okay, so then what does that do to my hydrogen? Gives me 12, so I want to put a 6 here, right? So how many total oxygen do I have over here? 16. So what does that mean that one has to be? Has to be a 4. So I would take that and say it's H3PO4. So I have to work a little backwards on that way. Okay? Does that make sense? Yes? Okay. So that leaves you with your packet that you can start working those 2 sections. And tomorrow we will be doing a single replacement.